So good afternoon to those that are in Europe. It's good morning for me here in New Zealand. So welcome to our first ISBF TERMIS joint webinar session for today. And my name is Kun Lim. I'm from the University of Otago, representing ISBF Early Career Researcher along with Dr. Ricardo Lobato here from UMCU Utrecht, Dr. Shrek Zhang from Harvard Medical School, and Dr. Andrew Daly from NUI Galway. And today we are also joined with Professor Lorenzo Moroni, who will be our keynote speaker today, and also Professor Jeff Richards, who currently is our TERMIS Global President. So Jeff will start the session with giving us a warm introduction, and I'll pass the forum to you, Jeff, please.
Thank you, Kun. So I really want to welcome everyone to this session. I think this is a great initiative to connect two really strong societies together. And I'm hoping this will be a long-term relationship between TERMIS and ISBF. And first, or mainly, I want to thank one person who's been working for both societies to get this together, and at the same time trying to arrange a World Congress for TERMIS. So Lorenzo has worked very hard to get this together, and I thank you for that. We'll have a memorandum of understanding because of his work there. And I really think this is a good way forward. ISBF and TERMIS will be able to work together extremely well. So thank you, Lorenzo. And it's really great to see all these young investigators and students promoting and moving this forward. So let's work together. It's always stronger together. Thank you.
Thanks a lot, Jeff. So Professor James, you also wants to convey his introduction as well. Sorry, I had to share it with the sound on. So he sent through a small video, and I'll just play that on his behalf.
Greetings. My name is James Yu.
Sorry about that. Some technical issues going.
Always tricky when you go live.
Yeah. Let me try to share it again. Sorry, Lorenzo, we're taking off some time from you.
No worries. I'm a fast speaker. Hopefully everybody will get through my Italian accent.
Greetings. My name is James Yu, and I serve as the current president of the International Society for Biofabrication. On behalf of ISBF, I would like to share our excitement with you about the collaboration between the TERMIS and ISBF. As you know, many members of both societies have actively participated and contributed scientifically by sharing their work and knowledge in both societies' scientific events at various levels. However, this ISBF TERMIS virtual webinar series marks the official start of a long journey together. I would like to thank Professor Lorenzo Moroni and the Society's External Affairs Committee for cementing the collaboration between the two societies through the MOU that was signed last year. We look toward expanding the collaboration to other society functions in the coming years. Thank you for your attention.
So thank you, James. James can't be here with us today. And I'll pass it on to you, Ricardo, to introduce Lorenzo.
Sure. So thank you, everybody, for joining us today. Before we start, we'll just read a little bit of housekeeping rules. If you have a question, please feel free to write them anytime in the chat, and we will pose those questions in the Q&A session at the end of the session to Professor Lorenzo Moroni. Likewise, after the presentation of the keynote from Professor Moroni, there will be 3 selected young scientists from the abstract that we received that will be also presenting their work. And there will be a second Q&A session that will be chaired by our colleague from TERMIS, Lisette Tomo. Without further ado, let me introduce Professor Lorenzo Moroni, who is Professor of Biofabrication for Regenerative Medicine at Maastricht University. And he also is also chair of the Complex Tissue Regeneration Department, and is vice rector of Merlin, the institute based in Maastricht indeed. And by the way, he's also the co-chair of the upcoming World TERMIS Congress, as you can see probably also from his background. Lorenzo is an expert in both biofabrication and regenerative medicine. He holds a PhD from the University of Twente. And over the course of his career, he has worked at many places around the world, including the Technical University of Milan, Chalmers Technical University in Sweden, University of California, Berkeley, Johns Hopkins University, and the Orthopedics Institute in Rizzoli before going back to the Netherlands and then eventually now settling in Maastricht. His research bridges biofabrication technologies to generate libraries of 3D scaffold to control cell fate. And this also translates to design of biomaterials, 3D scaffolds, and modification of surface properties to tune cell materials interactions. Without further ado, then I'll let the floor for Lorenzo for his talk, and we are very keen to hear what he is going to show us. Thank you, Lorenzo.
Thank you, Riccardo. Can you guys hear me well? Good. Thank you, Riccardo. Thank you for the kind introduction, and I also let me extend my gratitude also to Koen, Shrike, and Andy, and all the other members of the early career committee of the ISBF, as well as my thanks to the SYIS members of TERMIS. It's my pleasure actually to be here with you, and without actually any other further use in terms of introduction, let me just spend a couple of words on the 2 societies that are coming together today. Many of you probably have already been acquainted with the Tissue Engineering and Regenerative Medicine International Society, which is organized in 3 different continental chapters. We have recently changed the membership model here, so you have actually the opportunity to become a member of the society at any time during the year, in addition to the time that we host the conferences. Membership benefits are available at the website, and if you have any other question, please feel free also to contact Sarah Wilborn, who is our outstanding executive administrator at TERMIS. Likewise, the International Society for Biofabrication is also an intercontinental society. It is a little bit younger than TERMIS, and so we don't have yet a continental chapter subdivision. Also in this case, you see there the membership rates for senior and young members, and a number of different benefits that are included by becoming a member. So let me then jump a little bit to the scientific topic, actually, that I would like to talk to you today. This is going to be more of an educational talk, where I will still try to sneak in actually a couple of exciting data that we have been able to generate in our department. But I will also try my best to convey a personal overview of past successes, where we are at the present moment, and then some personal notes on where I see the field going into the future. And again, I underline that this is a personal note, because in 25 minutes, it's going to be impossible to give you an overview of all the wonderful work actually that is going on across the roads of biofabrication and tissue engineering and regenerative medicine. Together actually with a rather important and broad group of people across actually the globe, we have been revisiting actually the definition of biofabrication when applied to the term field a few years ago. In the meantime, also biofabrication is living an exciting moment in terms of applications that go behind tissue engineering and regenerative medicine. Examples are in soft robotics, in renewable energy resources, and in biosensors, for example. But today here we are focusing on tissue engineering and regenerative medicine applications, where actually the field has its roots. We have actually defined two main pillars, where either by bioprinting and therefore by directly in automated manner organize cells, materials, or biological factors in a specially organized manner, or by bioassembly, where actually we create more miniaturized Lego kind of Lego blocks. We can actually make more clinically relevant macroscopic tissues. In either of these two pillars, we foresee a phase where the constructs are actually matured in vitro and then are used either for implantation in the defected site we want to regenerate, or as a 3D in vitro model, for example, to understand better pathological conditions, or for screening possible other treatments, such as drugs in the case of pharma applications. Now, there is actually also a third exception to the rule, to the two pillars, which is actually where we consider acellular scaffolds that have instructive hierarchical or surface properties that are able actually to steer the activity of endogenous cells, and most likely endogenous stem cells, so that these constructs actually can be implanted directly into the site of need and activate the resident cells in that place. And so in these three different domains, typically additive manufacturing and electrospinning technologies have come more and more together as a common platform of technologies from which bioprinting and acellular constructs have their origins, whereas bottom-up approaches are typically what are used for bioassembly modalities. Within the park of additive manufacturing technologies, we have also tried to define a ratio, a so-called RTM ratio, where actually we compare the amount of deposited material, the volume of deposited material, with the resolution of the technologies in terms of minimum feature width. And we have used actually this kind of parameter to define the level of fidelity, as well as the speed of fabrication of the different kind of additive manufacturing technologies where biofabrication strategies take origin from. Most of you actually probably already know the classical palette of additive manufacturing technologies, coming probably from the very early days of 3D printing, where a binder is injected on top of a powder bed in a selective manner, to the classical group of extrusion-based systems, and to the more recently revived light-based system, either in terms of photocurable systems or selective laser sintering systems. All of these technologies are gathered by the same principles, where we start actually from a virtual object made on a computer-aided design software, which is then transferred to the software governing the additive manufacturing or rapid prototyping unit, which actually segments the object into layers that are then deposited in a sequential manner on top of each other. At least this is where most of the technologies come from. Again, here, in some cases, there are also some exceptions to the rule. Now, in terms of extrusion-based systems, you have also probably seen them called in literature with a number of different varieties of terminologies, from the more conventional fused deposition modeling to 3D fiber deposition, direct writing, direct printing, and so forth. Aside from the nomenclature, this is a classical technique where you have a continuous jet of material that is extruded from a nozzle by the application of a pressure, eventually either at room temperature or by applying also heating to actually heat a thermoplastic material above the melting temperature. These are systems that have a relatively high resolution, and actually probably are the group of technologies that is most versatile in terms of the palette of biomaterials that we can actually process. Still, they have certain disadvantages. They depend still on the viscosity of the material, although a number of advancements in this have been made. When applying heat, they are subjected to thermal degradation, and the fabrication speed is not the best of the work. We will again come back to that when looking at more recent technologies. So what are the possibilities that can be done to improve actually about the speed of this technology? This is actually nice work from already quite a few years ago from the group of Jennifer Lewis, where actually through microfluidic principles, they have been able to design new nozzles, enabling actually the position of multiple fibers in the same go. With similar principles, they have also created complex nozzles, again taking inspiration from microfluidic principles, where multi-materials now can be ejected in the same time, either by creating complex structures such as Janus fibers, or by really localizing and focalizing different materials in different areas, spatial areas of the same construct. Within the case of extrusion-based additive manufacturing modalities, there have also been wonderful work inspired by the lab of Skylar Tibbets at MIT, introducing the concept of stimuli-responsive 3D printing, or so-called many times 4D printing, where essentially a 3D printed object can deform its shape in time by being exposed to an external stimuli. So actually, when considering these different elements together, I would like to show a quick example of how a cellular constructs, cellular scaffolds can be created instructive to actually steer the behavior and activity of stem cells. In this case, actually, by taking inspiration to the dynamic loading that typically is applied to many of our tissues. In our specific case, we are going to talk about bone. Now, many times when we walk or when we run, we subject our bones to mostly compression and tension. We have actually thought whether we could use ultrasound stimulation to actually create that mechanical stimulation that would also allow us to change the morphology of the cells adhered on these kind of scaffolds, and then see if that actually would result into activating them into a specific pathway. Now, it is known actually from the clinic already that ultrasound stimulation is used in those fractures that are not able to heal by themselves, or so-called non-union fractures. And it is known actually that this system allows the activation of faster proliferation of resident cells. So we played a little bit to giving stem cells a different kind of music tunes, whether we wanted to know whether our cells like better classic or rock music. This actually was the work of a skilled former postdoc in the lab, Sandra Camarero Espinosa, who is now a group leader back in San Sebastian in Spain. And Sandra actually was interested to apply the principles of phase separation in material blends to create Janus-like fibers on the go as we were depositing the scaffolds. Now, if we do this by also taking the different physicochemical properties of common materials such as polylactic acid and polycaprolactone, Sandra was able to create a Janus-like fiber scaffold where PCl acted actually as the backing material and PLA as the actuating material. We were able to measure the actual vibration that were subjected to the scaffolds when applying a ultrasound field, which actually also correlated well with the modeling that we did about the setup. And actually, under stimulation with ultrasounds, our bone marrow-derived mesenchymal stromal cells were able to produce more fibronectin, more collagen type 1, and also to upregulate a number of different osteogenic markers, either general markers such as collagen 1 or collagen 10, early markers such as RANX2, or late markers such as osteocalcin. Ultimately, looking at mineralization, we were able to observe much more abundant mineral nodules in the Janus-like scaffolds and higher alizarin red staining, again, confirming the mineralization of the tissue formed by the stimulated cells. Another example of older technologies that are nowadays more and more used also in the case of bioprinting is actually coming from stereolithography, or in the case we use digital mirror arrays, called also digital light processing, where again here we basically create our construct by hitting a photocurable polymer in a specific pattern through a mask. Here we can actually have a higher resolution compared to extrusion-based systems, higher production speed, but typically, although again there have been a lot of improvements in the past 5 to 10 years, the amount of biomaterials that can be processed with this technology is still limited, and there is always the usual question whether the initiator that is used is potentially toxic. Again, although here also from an organic chemistry point of view, there have been a number of improvements in terms of biocompatibility of those initiators. In an acellular modality, these kind of scaffolds are clearly much more complex, can reach a much higher complexity than extrusion-based systems. Here again, you see some examples which again will give us geroid-like structures, or structures like in the previous slide that enable us to have negative Poisson ratios. The resolution, especially when moving to photon polymerization, can really increase to the nanoscale, to the submicron and few hundreds nanoscale meter level, where actually we can create now almost artificial microenvironments to mimic the microenvironments of single cells in our body. The same technology has been used by the group of Alexander Ovsyannikov in collaboration with Sandra van Vliebergen. Actually a beautiful example of the collaboration between the two societies to create actually a vasculature network inside an organ-on-chip device, which is actually personally one of the fields where I see more and more work upcoming in the near future. All right, so far we have just talked about a single tissues, and that's where typically acellular scaffolds, maybe with the exception of maybe 2 tissues together, where acellular scaffolds can really still steer the behavior of stem cells towards the wanted regeneration. However, if we look at our body in a more holistic manner, not just looking at complex organs, but also simply again taking the inspiration to our bones, where multiple cells are present actually to maintain the bone in a homeostatic manner, but also a number of accessory networks such as our blood vessels, our neural network, and lymphatic vessels are present, then actually other kind of biofabrication technologies would probably be more at use in this case. And that's where I think bioprinting could really play the difference. We have again a number of different ways that are used today to do bioprinting, starting actually from the classical inkjet bioprinting, which goes back into the luminal work of groups such as Vladimir Mironov, Gabor Forgacs, and Thomas Bolland, who are considered among the founding fathers of bioprinting in the field. To also again another droplet-based system such as laser-induced forward transfer, where scientists such as Fabien Guillemot and Boris Chichkov have been doing wonderful work to again some of the most used technologies that go under robotic dispensing, where again a number of different labs around the world are active on. In all these varieties of bioprinting, we typically always consider whether we want to have the cross-linking of the hydrogel carrying the cells that we are interested into, either before, during, or after the processing. A few other technologies are arising actually in the context of bioprinting. Again, here is an example of levitation-based modalities. Which actually is quite interesting, because in this case we can, or we would be able in the future to deposit in space against actually gravity different kind of cellular aggregates, ultimately maybe even organoids of different origins, and therefore maybe really mimicking also that heterogeneity of how many type of specialized cells are organized in organs. So again, here I would like to show just a couple of very old studies how the field has started. This is from the group of Gabor Forgacs, where actually hydrogens were not used to carry cells, but only as a template to then deposit cellular spheroids to create a construct of interest. This could be used, for example, to create vascular constructs. And you see here that through the fusion of different spheroids, it was possible to create also relatively small and branched complex vasculature. The group of Forgacs was also interested in creating biological neural guides, which actually, when implanted into a rodent model, were able to significantly improve the rate of nerve regeneration. Here in the histology slide shown by the several different black dots coming through the neural conduit and exemplifying actually the amount of neurites that were regenerated and bridging the two distal parts of the nerve defect. A few years later, actually, the work of Dongbo Cho at Post-Tech University was among the first to introduce the concept of using the cellularized DCM as a bioink for bioprinting. And actually, one of the first to also introduce the concept of hybrid biofabrication, where acellular scaffolds were combined with bioprinted constructs, in this case, actually to provide more mechanical stability to the cellularized DCM bioprinted constructs, actually. This concept was also taken further from Wake Forest Institute, from the group of James Yeo, who actually showed in 3 different cases, in the case of skull defect, in auricular defect, and interestingly also in the case of a neuromuscular junction, that it was possible to functionally regenerate this kind of tissues. Interestingly also, this was one of the first paper showing also the capacity of this technology to create really human-scaled constructs. Along the same line, and to give you also a few other examples of how biofabrication technologies could be useful for upscaling the size of engineered tissues is provided actually by the classical template leaching modality, originally developed by Jordan Miller and then used by a number of different people around the world. In this case, actually, again, a study from the group of Jennifer Lewis, was the first one showing actually the capacity of maintaining perfused and alive a 1 cubic centimeter construct of a bone tissue. Talking about template leaching, I could not talk about the work of Jordan, who has really been the scientist that was the most transformative about this technology. Again, many of you probably are familiar with the most recent work of his, where he has been able really to implement much more complex vascular structures, able also to provide different kind of oxygen levels, such as then in applications or in meaningful applications, such as the vasculature of our lungs, but also in terms of creating a functional tissue, as depicted here on the upper figure, in case of a liver vascularized construct that was implanted back into an animal model and showed the functionality. So where actually are we going in the future with bioprinting? I think a lot of interest is also, excuse me, in the field of trying to deliver this technology directly on the patient with so-called in situ bioprinting. Here again, you see a sort of fantascientific cartoon, if you wish. For those of you that have seen the Sixth Sense film of Luc Besson, you might remind actually some scenes of that movie, where actually the idea would be to have a device that with different cartridges having different kind of bioinks, we would be able to directly print on top of a defect, either a topical defect, such as in the case of the leg, or a more complex defect in the case of our eyes. And again, this actually is a work that has been already proved by the group of James Yeo in the case of wound healing constructs. But what actually I would like to show you is perhaps a paper that was less or might be less known, which I find fantastic. This actually is the work of Nicola Elvasore in University of Padova in Italy, where they used actually the concept of two-photon polymerization to create a so-called intravital bioprinting modality, where here the construct actually can be directly printed behind the skin by applying again two-photon polymerization principles, in principle without actually any sort of surgery. And so they have also used this technology for the regeneration of a neuromuscular junction, and actually showed in a rodent model it was possible to recover actually the functionality of a paralyzed limb. Questions that are, I think, still open in the field is which kind of cells should we use? Should we go to pluripotent stem cells in the case of multicellular organs? And if so, how actually can we direct pluripotent stem cells into the different kind of specialized cells that are in multicellular organs, such as kidneys, for example, which is comprised of more than 20 type of cells. Which kind of scaffold in case of acellular scaffolds, but also which kind of biological construct should we print, and which kind of technology should we use? I mean, every body has its own favorite technology, and there are nowadays a number of different techniques available with their advantages and disadvantages. I'm actually towards the end of my presentation. See, I'm already a little bit too late. One other thing that it's important for us to think about is also the dynamicity of our tissues. And so oftentimes we use hydrogels that are still not capturing that dynamicity. And again, here I would like to show some of the work we do at the department in collaboration with a group of Matt Baker, where we are able actually to put on relatively simple alginate macromolecules, which normally are static hydrogels, dynamic cross-linkers that actually turn these hydrogels into supramolecular hydrogels that are able to self-heal, can be bioprintable, and actually can change the morphology of the encapsulated cells from completely rounded to completely spread, just simply by changing the level of dynamicity of these cross-linkers used. We use this kind of hydrogels as well as conventional hydrogels on a number of different applications from a bioprinting perspective, where we focus mostly on organ systems. We have done in the past some work in the context of islet of Langerhans, and nowadays are focusing more on cardiac thyroid and kidney models, where actually Carlos Mota, who is another PI in the department, takes the lead. It will be also important in the future to go more and more towards multi-material bioprinting, because most likely there will not be a magic bullet in terms of hydrogel network for any sort of cells of our body. Therefore, we will have a specific customization of biomaterial and cells. In terms of speed, we will also have to continue progressing. Here again, you see a number of different techniques that have been developed in the past. Some of the work nowadays is also already used by other labs, such as the work of Adam Feinberg on the fresh bioprinting concept, or the work of Thomas Angelini on granular bioprinting. In terms of photo bioprinting, actually, the work of Ricardo himself has been really transformative in the past years in terms of providing speed to the technology. And in terms of versatility of multi-component bioprinting, the work of Shrike Zhang has been also quite transformative in the past couple of years. The last minute is actually to just give you a brief introduction to bioassembly. Here, actually, I would refer you to the wonderful work of Soji Takeuchi at University of Tokyo, where again, as I said at the beginning, different kind of mini Lego-like blocks can be designed and then placed together to then create a more macroscopic structure. Here again, in this context, I'll just show you a short educational video of something we have developed ourselves in collaboration with a group of Roman Truckenmuller here at Merlin, where actually instead of gels, we used micro objects that were put together with the stem cells. And by changing the shape and size of these micro objects, we were able to create injectable paste, again, looking at skeletal regeneration. All right, with this, I am at the end. I'd like to again thank you all for your attention. I'd like to introduce a number of people that are within the department, who comprise now 4 different PIs and therefore 4 different research groups. Here you see the faces and the names. Thanks also to the funding bodies. And again, before leaving you, I'd like also to remind you about the 2 main events of the 2 societies this year, the Biofabrication 2021 conference in Wollongong, and of course, the World TERMIS here in Maastricht in mid-November, where I really hope to wholeheartedly welcome you face-to-face there. Thank you.
Thank you, Lorenzo. Thank you very much for this inspiring talk. There are a couple of questions. I will leave the floor to you, Shrike, for that.
Sure. Yeah, thanks a lot for the wonderful talk, Lorenzo. So there are a couple questions, if you don't mind. So one by Rong Wang, basically asking about the genus structure in the 4D printing that you mentioned. And he was wondering about whether control experiments on different ratios of PCL, PLA versus genus structure were performed regarding cell behaviors and ultrasound defection.
No, we have, once we have actually created the Janus fibers with the 50-50 composition, we have then carried on with that. We don't expect actually to have any stimulation on it might actually be that we will have actually more different kind of stimulation with the higher amount of the PLA composition, but not certainly with the lowest amount of them. But again, that's a good point. Actually, maybe something also to look into. But yeah, we have once we have actually had the complete Janus fibers with a 50-50 composition, we have then carried on with that.
All right, cool, thanks. And Paul had a question on whether a bioprinting structure or construct has ever been implanted in human to date, or basically translational potential of these bioprinted constructs.
Not that I know, and that indeed would be one of the next challenges and one of the next things that as a community we should deliver. That I think they have reached the stage of large animal trials, but there is not yet a clinical trial that I am aware of with the bioprinted construct.
Maybe just to follow up on that very briefly, then in your view, what are we missing to get to that point? It's just a matter of time, or?
Yeah, I think that's a good question. I think it will depend a lot from the application. I think for organ-like structures, we are very far away, right? I mean, I always say that, you know, for now, I think we are doing a good job in terms of creating 3D in vitro models, but for a real, you know, an organ patch, you know, I would love to see that something in the clinic by the time that I get retired. So it will be a few more years down the road. In case of maybe simpler structures such as skeletal tissues, I think we are actually not that far from it. I think again the work, for example, that is done in the group of Jos Malda in Utrecht is definitely getting closer to that. I'm not 100% sure actually in the case of skeletal tissues what we are really missing. Probably not really a lot. It might be more mechanical durability of the constructs, but also there I think we are making progress. It might be challenging actually to have comparative studies where there are already other kind of maybe more classical biomaterial solutions, such as I'm again talking about bone, the case of osteoinductive ceramics, where actually we would be able to prove the fact that really bioprinted constructs are needed. But I think if that is shown, the next step should really be probably going to the clinic.
Thanks.
All right, so there actually one more question from Isabella. So the question was, so combination of bioreactors and bioprinting. So what are your views on that? I mean, where we are right now and what are the futures over there?
Yeah, I think it's also done. I again, for time, I have not put it in the presentation, but certainly there have been a few attempts on basically fabricating a bioreactor and the construct within the bioreactor itself. I think certainly would be an interesting direction to go forward, especially when we will need to have a tissue maturation stage of the construct, and then actually having a customized bioreactor for those constructs would be definitely important. Now, again, this would be from a more scientific point of view. If we then have something that is very successful and we want to upscale it to the clinic, I'm not 100% sure if having such a customizable construct in a bioreactor strategy would be the best way forward, but that's simply more from a cost-effective point of view than actually a personal scientific interest, which if would be that only, I think definitely would be the route to go.
All right, cool. Thanks very much again for the wonderful talk, Lorenzo.
Thank you guys again for organizing the webinar. Looking forward for the next speakers.